Hi, everybody. Welcome to our first round of IRISEP Fellows introductory presentations. We have 10 5-minute talks today where the fellows are introduce themselves and their projects. So first up, we have Amaya. You can see his slides are on the screen. So whenever you're ready to get started, Amaya.
Yeah, thanks, Mr. So hi everyone, my name is Amaya Thete and I'm a senior undergraduate at BITS Pilani Goa campus, India. My project over the summer as an IRISEP fellow would be to explore equivariant graph neural networks for charged particle tracking. Over the course of the project, I'll be mentored by Dr. Savannah Theis from Princeton and Dr. Daniel Minane from Berkeley Lab. To really understand what the entire project is about, it really helps to break down the title into chunks and then look at each part separately. So let's get started. So let's see really first what charged particle tracking really means. Proton collisions at the Large Hadron Collider produce thousands of particles. And out of these particles, we find that the charged particles, or rather particles which are charged, travel in curved tracks throughout the detector's magnetic field because of the Lorentz force. While doing so, they leave energy deposits in the tracker layers, and these deposits are called hits. Now, these hits are basically what the evidence of the track is. Now, the goal of track reconstruction is, given a set of hits in the tracker, we want to assign labels to each hit. Eventually, what we want is all hits belonging to a particle need to share the same unique label. Thus, if you see, in a way, we are clustering out our hits to trace out the trajectories of the particle. And the picture over here is a really pretty art installation made by Yannick Perkis, a PhD student at Stanford, as part of her a course project. What you can see here is at the center of the picture, that's where the collision happened, and these fluorescent lights, you can see they represent the particle tracks. While this is all nice and fun, current track reconstruction algorithms scale very poorly with detector occupancy and therefore would be unsuitable for high luminosity applications. So this motivates the search for better algorithms. And what we find is machine learning based reconstruction algorithms have shown shown a lot of promise. Now the next question is, how really do GNNs fit here? But before we talk about the algorithm itself, let's talk a bit about the representation of tracks, because the representation can help us define how to process the event. What we see here is that tracking data can naturally be represented as graphs by identifying the nodes with hits and the track segments as edges between these hits. The picture you see on the right over here provides a concrete example of this, where these red dots you see on the left-hand side are the hits in the tracker layers, and on the right you can see a graph that has been constructed from these hits. Another advantage of graphs is that they can also inherently capture much of the sparsity that is pervasive throughout the tracking data. So tracking data is inherently sparse, and out of the entire detector, or rather the tracker that is present throughout the detector, you will find only so many hits as compared to the entire length of the detector. So that's what we mean really by sparse data. And graphs inherently can capture this sparse data very well. And also they capture the relational structure of the physical data in a pretty advantageous manner. Now, when we want to deal with graph structured data, there's a class of geometric deep learning algorithms called graph neural networks, or GNNs for short. Recent work has demonstrated that graph neural networks are quite suitable for particle tracking applications. These two particular references are what I'm talking about. And they exhibit competitive, if not better, performance than the extent counterparts, which are mostly based on Kalman filter tracking algorithms. So now coming to the crux of the project, equivariance. Most GNNs that are developed are permutation invariant, which means that the output which the network produces does not depend on the order in which the input is fed to the network. And this has been very well studied. However, there hasn't been much study into explicitly looking at other forms of equivariance, particularly in the context of particle physics. What we can actually sometimes do is we can encode other forms of equivariances into the GNN architecture to force the model to follow a certain symmetry group. Theoretically, what this does is it reduces the model's hypothesis space and therefore in a way reduces the complexity of the model, and which eventually reduces the training and inference times. Since tracking data follows Euclidean invariance, that is E3 equivariance, we posit that incorporating this equivariance into the model architecture would in a way reduce inference times, obviously, but it would do so while retaining the model's expressive power. So we're really not compromising on the performance of the model, but we're instead just focusing on reducing how long it takes to make or rather construct a track, because at the high luminosity LHC, you're going to have millions of particles that are being produced, and you need to do this process really quickly. And the inference time needs to be really, really small for it to produce any, what do you say, meaningful results. Therefore, the plan in this project, as I discussed, is to study equivariance in the GNN architecture in the context of particle physics. And we want to do so by building upon the VecNet architecture, which was developed by IRIS-CEP fellow Jason Wong last year. Jason developed an equivariant model for jet tagging. So what we want to do is we just want to modify that architecture such that it supports the particle tracking application. And then we want to see how we can explicitly add Euclidean or E3 equivariance into the model. So that is all I had for today. Thank you for listening. If you have any questions, I'll be welcome to take them.
Okay, thank you, Amaya. Up next, we have Aryan. You want to share your slides, Aryan?
Hey, yeah, just give me a minute.
Sure.
Okay, can you see my slides?
Yep, perfect.
Okay, so I'll start off with an introduction. Hello, everyone. My name is Aryan. I am an undergraduate student at Manipal Institute of Technology, and I'm currently majoring in computer and communication engineering. And this summer, I'll be working on the project titled Accelerating Uproot with Awkward Forth. And my mentor will be Dr. Jim Pewarsky from Princeton University, who has also mentored me last year. So, so let's see what this project is really about. And for me to explain what I'm doing here, I need to explain first what Awkward Forth is. So Awkward Forth is a DSL, or a domain-specific language, which is built into Awkward Array, which is again a package in Scikit-Learn. So the thing about Awkward Forth is that it's a really low-level language, and it works in some ways like assembly. There's only one data structure that is available to you, which is a stack, and you can only put on integers onto the stack. So Awkward Forth code is really, composed of these small bits of instructions. And one advantage of that is it's really fast. So Awkward Array comes with the compiler, the parser, and everything that you need to run Awkward Forth code. And we sort of make use of the fact that Awkward Array has all this to make a file reader. So root files are really widely used in particle physics. And there was this paper, the archive number of the paper is listed in the slides, which studied the possibility of a Awkward Forth based file reader for different kinds of file types. And one of them was Avro. So in the months leading up to this summer, what I did was I worked on this Avro reader. And as you can see, the paper describes the observed performance of a Forth-based reader for Avro files. And I'm really happy to report that just last week we achieved this performance, which is really remarkable because in some cases it's a factor of 10 increase in performance over fast Avro, which is the gold standard for reading Avro files. So, Awkward Array now has an Avro reader which is faster than any Avro file reader that we have tested. So kind of extrapolating from this, we also have this, another study in the same paper, which tries to see how much of a performance gain we can get with a awkward forth based root file reader. And this is what I'm currently working on, and hopefully we will be able to achieve the same kind of results that we did with the Avro reader. So yeah, that's about it. And yeah, thank you for listening.
All right, thank you, Aryan. Next up is Debar.
Yeah, so just give me a minute. I'll be sharing my screen.
Sure.
Yeah, just let me know if it's visible.
Yep.
Great. Okay, so hello everyone. About myself, I'm Durbar Chakrabarti, presently a sophomore pursuing an undergraduate degree in computer science engineering from National Institute of Technology, Durgapur, India. And over the course of this summer, I'll be working on the project for defining metrics for user engagement activities on the Coffee Casa analysis facility deployments. And for this project, my mentors would be Oksana Sadura and Ken Bloom. So let's get started. So just a brief summary about the project. So Coffee is one of the major Python packages which are developed by the IDSAP analysis systems domain, and it is a columnar object framework which is meant for analysis to enhance data analysis functionalities on Python for HAP event data. And Coffee can be deployed and used at Coffee Casa analysis facility. So this project aims to define a set of various user engagement metrics based on the data collected across various platforms, including Jupyter Hub, Dask, Kubernetes clusters, and etc. for Coffee Casa facility. So we'll be trying to define a package, AF Metrics, which will automate this entire monitoring process as well as the data collection process for this purpose. Moving on. So the proposed infrastructure is as presented here. So what we are planning to add to the existing infrastructure is, as I mentioned before, we'll be including this AF metrics package, which will be connected, as it stands right now, it's connected to Jupyter Hub as well as Dask Scheduler and Dask Workers. And in future, it might be connecting to the other elements of the infrastructure, including Conda, Skyhook, Xcache, etc. That depends on how the project progresses over the course of this summer. So moving on. Yeah, these are the various components of the Coffee Casa analysis facility. And in this project, we'll be working on the Jupyter Hub parallel processors and Dask scheduler interface, as well as we have worked on these three components. And in future, if time permits, then we'll be looking into the Kubernetes scale out as well as the HD Conda scale out. So let's just have a look at some of the stuffs that we have achieved so far. One of the primary achievements is that we have been able to locally host Jupyter Hub and Dask and connect them to Prometheus monitoring tool and visualize the results of these telemetry operations using Grafana dashboards. We have also been able to define custom metrics, which are not inherently provided in the corresponding metrics endpoints of these of the said platforms for a custom machine learning model and monitor the user-defined metrics. And only recently, we have also built a Python script with user-defined functions and Dockerized this entire script with Prometheus and Grafana, such that upon running the entire container, the monitoring process gets automated. And these are just some of the metrics we have analyzed in addition to others. These are some of the more useful metrics, rather. So the Jupyter Hub metrics, as you can see, they are listed as follows, as well as the functionalities of each metrics are attached against the name of the metrics. And in addition to the Jupyter Hub metrics, we have also listed some of the Dask metrics we have been able to analyze. And in future, we aim to package this entire script such that it can be run on any facility without having to locally set up all the tools individually, for instance, Prometheus, Grafana, etc. And we are also targeting to implement and test and host the package setup on the UNL infrastructure. And we'll also be testing the user experience on the CoffeeCache analysis facility. And in addition to that, we'll be making the setup scalable so that it manages to function even in case of large data set which is to be monitored, which will be the case in its future configurations. And that was all from my side. And if you wish to look into more details regarding the work we have been doing during the course of this summer, then feel free to check out the following repositories. So thank you. That's all.
Thank you, Devar. Next up, we have Catherine.
Yep. All right, give me a second to share my screen.
Sure.
All right, can everyone see it?
Yep.
All right. So hi, my name is Katie Edwards. I'm a student at Iowa State University studying aerospace engineering. I just finished my first year at Iowa State. The title of my project is Geometric Machine Learning with Dune. I have 3 mentors for this project: Dr. Jane Nachman from the University of Iowa, Dr. Jin Tian from Iowa State University, and Dr. Hangyang Gao, also from Iowa State University. In addition, I'm also collaborating with a group of students from the University of Iowa who are working on different but similar projects. They're using the same machine learning algorithms that I'm using, but for different purposes. So for a little bit of background, neutrino interactions are generally pretty weak and it makes them hard to detect. One way of detecting them is using a liquid argon time projection chamber, or LARTPC, which is basically just what it sounds. It's a chamber with many tons of liquid argon in it that is used to take images of neutrino interactions. And for the DUNE project specifically, there's a near detector and a far detector. The near detector is located at Fermilab's site in Batavia, Illinois, and the far detector is in South Dakota. And the purpose of the DUNE project is to determine which neutrinos have oscillated from the near detector to the far detector. So they send through a stream of muon neutrinos through the near detector and the far detector and take images at both to determine which neutrinos have oscillated or changed flavor. So since they start as muon neutrinos, they could end up at the far detector as electron or tau neutrinos. The machine learning algorithms that I'm using for this project are in a GitHub repository called LARTPC MLReco 3D. And the algorithms in this set are used to identify different structures of neutrino interactions, such as tracks, showers, and shells, which are formed from muon decay, delta rays, and sometimes ghost points. And many of those structures can be seen on the image to the right, which is from a simulated liquid argon time projection chamber image. So ghost points are a little bit troublesome with geometric machine learning. They're formed when a series of 2D images are turned into one 3D image. And generally for liquid argon time projection chambers, images are taken as multiple 2D images taken from 3 different angles that can be compiled into a 3D image using an algorithm called Cluster 3D. However, the algorithm isn't perfect, so it often spits out some ghost points that are not actually part of the neutrino interaction, but are still shown in the image. So one part of geometric machine learning algorithms is weeding out those ghost points, so only the true data is analyzed. So my main goal for this project is to identify and make improvements to the reconstruction algorithms in the GitHub repository that I mentioned before. And I'll be training these algorithms using data from deeplearnedphysics.org, which has public data sets from liquid argon time projection chambers. And at the end of my project, I plan to compare the performance of my modified geometric machine learning algorithms to convolutional neural networks, since they have different strategies of analyzing neutrino interactions. Thank you for listening to my presentation. Are there any questions?
All right. Thank you, Katie. That was next up. Manvasi.
Hi, I'll be sharing my screen.
Sure.
Is it visible?
Yes.
So hi everyone, I'm Manasvi, an undergraduate student from Delhi Technological University, and I have been working as an IRIS-CEP fellow for the last few weeks on the project Accelerating Offered Array Builders under the mentorship of Diana Osborne and Jim Pivarsky from Princeton University. So I'll be starting by giving a brief overview. Offered array is a library for nested variable size data, including arbitrary length lists, records, mixed types, and missing data used to manipulate JSON-like data using NumPy-like idioms. Offered arrays are not only more concise, using idioms familiar from NumPy, but they are much faster and use less memory than the equivalent Python expression. So my project aims to accelerate the performance of array builders used by Offered Array by preventing unnecessary memory copies in growable buffer, optimize allocation of memory, and improving the speeds by specifying the array builder type in advance in the layout builder. So initially, the plan was to modify the existing code of layout builder and growable buffer to achieve the enhancement in performance. But as it turns out, the new growable buffer and layout builder is going to be useful for another project by particle astrophysicists, which will be using offered arrays. So the easiest way for them to get offered arrays is to use a layout builder to fill some buffers and then send that to Python through Pybind 11. So to integrate it into their workflow, the layout builder needs to be templated, independent piece of C++ code, which is easily separable from the rest of the offered C++ code base and implemented entirely in the header files. Earlier, the layout builder used both buffer, but now it will be using growable buffers. So the growable buffer will also need to be header only. A mini package containing the layout builder and growable buffer header files will reside in a separate directory and can be dropped into a large C++ project easily, allowing offered arrays to be used in an external project without linking to the offered libraries. Generating all the types via templates will make it easier to dynamically generate layout builder from strings in Python and then compiling it with Cling. So I have almost finished working on the header-only growable buffer, which uses the multiple panels approach with the pull request in place. But before talking about the new growable buffer, let's have a look at the current implementation of growable buffer and its shortcomings with the help of an illustrative example. So in this example, we have initially reserved 5 slots for the buffer with a resize factor of 1.5 and the following array of data to be added. Initially, the growable buffer constructor is called, which creates an empty buffer with a reserved number of slots. The append function inserts one datum into the buffer and increases its length by 1. This is continued till the value of length is less than reserved. Once the value of length is equal to the value of reserved, reallocation is triggered by the setReserve function, which changes the value of reserved by multiplying it with the resize factor and taking the ceil value. So a new pointer is allocated. A copy operation is performed, which copies the previously added elements into the reallocated buffer. And after that, the append operation is continued. Similarly, the length again equal to the reserved value. Reallocation and copying are done and the rest of the elements are appended. So as we saw, to grow the growable buffer, the current approach reallocates and copies the buffer every time it gets filled so that the array remains contiguous. But as the size of the data increases, the performance reduces rapidly due to the repeated reallocation and copy operations and creates unnecessary memory copies. To solve this problem, I have modified the growable buffer to use multiple panels approach. So in the new implementation, instead of having just one pointer, I have used a vector of unique pointers, and each pointer points to a panel. In this approach, the growable buffer constructor allocates an empty panel with the reserved number of slots and appends data one by one into the buffer till the value of length is less than reserved, just like the previous case. But instead of reallocating and copying, a new buffer of the same size as the previous panel is allocated and the remaining data is appended in it. Once this panel is also filled, another panel is allocated and rest of the data is appended in. So the reason why the multiple panels approach is expected to be a step up in the performance is that the growable buffer is used to produce snapshots of the accumulated data by converting them into awkward arrays. So the external code copies the data out of a growable buffer so that it can own it. And since we have to do a copy operation anyway, we can combine it with the concatenate operation too. With the concatenation being free and having no extra performance cost, we don't necessarily need the buffer to be contiguous and can let it be discontiguous as it grows to avoid more expensive ways of growing a buffer like reallocating and copying. So I have also written some C++ unit tests to make sure that the new implementation is giving the expected results. These tests will reside in a separate directory called test-cpp. Here I have shown the test for complex and float data type. In the test, the array elements are appended in the buffer using the panels approach. An external pointer copies and concatenates the panels, and the result is checked against the expected output. I have already made a pull request for the same, containing the header only implementation of growable buffer and a unit test. So moving forward, I will start working on developing the templated header only layout builder, which will be using the new growable buffer. And since the growable buffer is rewritten as header only, the array builder code also needs to be modified to be able to use the new growable buffer. And currently the user can only add one element at a time, and to add an array, they need to iterate over it. So to allow them to have an option to add an entire array at a time by sending a pointer to the array and the array size as the parameters, functions like append can be overloaded. I will also be writing some more C++ unit tests for the layout builder and array builder. I will also write some performance comparison tests with the new code and the current code. The C++ code also needs to be integrated with the Python code. We also plan to submit an abstract to the Advanced Computing and Analysis Technique conference. So working as an IRIS Help Fellow for the past few weeks has been a great learning experience for me, and I hope to continue the same learning and do some good work. Thank you very much. Are there any questions? I'll be happy to take them.
Thank you, Mombasi. Up next is Max.
Yes. Can you see the screen?
Yes, we can.
Hello, everyone. I'm Max. I'm a second-year undergraduate majoring in physics at UC Berkeley. My project this summer is to conduct exploratory research into a machine learning approach to Kalman filtering in track reconstruction. My mentors will be Johannes Wagner, Louis-Guillaume Gagnon, and Professor Heather Gray. I will also be working with the group's tracking group for ACTS. The Kalman filter is a deterministic algorithm that combines predicted and observed states. At a high level, it does this by weighting predictions and observations by their uncertainty. Kalman filtering is used in a wide range of fields, but in high energy physics in particular, it's used as a part of one of the older and most reliable approaches to track reconstruction, which in this context is to propagate track states from track seeds to other detector layers, as well as smooth track candidates to get track parameters. This is in fact how it's implemented in the ATLAS experiment and ACTS. While the traditional Kalman filter has demonstrated great success for over 30 years, there are some challenges expected as data flow from high energy experiment grows. One, propagation often requires solving for equations of motion in homogeneous magnetic fields that we have inside the detectors. And this has to be done numerically, which means that the algorithm doesn't scale well as the number of hits increases on the detector layers. Our goal for this project is to develop a machine learning algorithm that embeds the properties of the Kalman filter such that the desirable properties are attained and efficiency is hopefully improved. Since this research is exploratory, we will look for different neural network architectures that can be applied to the problem. We have been working in other fields that have shown promise in things like recurrent neural networks for learning Kalman filters. Although these often approach to different challenges, such as nonlinear observations that we aren't dealing with, but the consensus is that it's not an intractable problem. Thank you.
All right. Thank you, Max. Next up is Natalie.
Yes, hi. Okay, hopefully you can see that.
Yep.
Okay, so hi, I'm Natalie, and my project is working on a muon collider tracking software. I'm going to be a third-year physics major at UC Berkeley this fall, and my mentors are Carol Kriska, Sergio Gendariani, and Simone Pagan-Griso. So some background on the project is that a proposed muon collider is a promising option for future high-energy physics experiments because muons have certain properties that create very high-energy collisions, so there's a lot of scientific potential. However, muons decay extremely quickly with a lifetime of about 2 microseconds, and this decay produces a lot of extra particles, which are known as beam-induced background, or BIB. So this is a simulated image of what the beam-induced background looks like. You can see that there are a lot of particles pictured here, and the different colors represent different decay products, which include photons, neutrons, electrons, and positrons. You can see there are a lot of extra particles, and this is from only a couple muons decaying in the collider. This is a closer image of the interaction point, and you can see that the detector is designed to block some of the beam-induced background, but there are still extra particles that obscure the collision products, which are what we're actually interested in studying. So the goal of this project is to optimize the tracking algorithm to differentiate between fake tracks caused by the beam-induced background and real tracks from collision products. An example of how we might do that is looking at plots like these. So these are just some standard histograms that I've plotted, and you can see that the beam-induced background particles, which are pictured in orange, tend to have a low momentum compared to the real tracks, and they tend to have less hits on the detectors than the real tracks. So we can go back and tell the tracking algorithm to filter based on parameters like momentum or number of hits, and hopefully we reduce the number of fake tracks. A constraint is that we also want to keep the efficiency relatively high, which means we don't want to miss a lot of real tracks. And this is a current efficiency plot. You can see that without beam-induced background, the efficiency is basically 1, and with beam-induced background, it's still relatively high. So it'll be important to keep making these efficiency plots as we make changes to the algorithms to make sure that it's still working. Yeah, so that's a summary of my project. Thank you for listening.
Oh, thank you, Natalie. Up next, we have Philip.
Thank you. Let me just share my screen. And can you all see that?
Yes.
Perfect. So hello, everyone. My name's Philip Templeman. I'm from San Antonio, Texas. I'm going to be a second year at the University of Notre Dame, where I'm studying physics and math. And this summer, I'm working on analysis preservation with my mentor, Dr. Kyle Cranmer. And just about my project, I'm building a workflow for the Minerva analysis. So if you look on the left of the screen, you can see the Minerva detector. That's a neutrino detector up at Fermilab. So it's analyzing a neutrino beam coming out of the main injector at Fermilab. And that hexagonal detector, those neutrinos are going to interact with atomic nuclei in there. And that's going to happen in a charge current interaction that will produce the neutrino's corresponding lepton. That's usually a muon, as well as a pion, which we can track using Minerva's scintillator detectors. The interesting thing about those is they're actually in 3 different orientations because of that hexagonal shape. So we can get a pretty accurate recording of their tracks. And the way that analysis works is all that data is both recorded as real data, but we also make Monte Carlo simulations of it while we're running the experiment. So we take those inputs and first we analyze them to create histograms of our data, which will turn into cross sections. So what I'm doing is I'm taking that analysis structure and I'm turning it into a workflow with the workflow language Yardage. And what a workflow is we break down that analysis into really small portions that we call pactivities. And in that we're just running a few steps of code. And for example, one major part of this analysis is called the event loop. And that's where we're looping through all of the input runs through each of the analysis variables we're using. And that's a pretty intensive process. So if we break that down into one run at a time and send that to a cluster of computers, we can really improve the runtime of this analysis. So that's what I'm doing using the computer clusters at Rihanna. We send the pactivities one at a time over there. And it is interesting to note the way that this analysis is currently done also uses a grid of computers that's located at Fermilab. They're really only using that grid for the event loop. So the part of the analysis that takes the most computing power. But what I'm doing is I'm going to turn this analysis into one that we can compute totally using a cluster of computers. And that really helps with analysis preservation because it means in the future when our dependence software gets updated, this analysis will still work because what I'm doing is I'm working on containerizing this software. So future versions won't mess it up. We'll preserve the old ones. That way in the future, we can build new analyses off of these, which we know will function. So do you guys have any questions? If not, thank you for listening to my talk.
Thank you, Philip. Next up is Jay.
Sure. All right, let me know when you can see the screen.
Yes, yep.
All right, hi everyone. I'm Jay Gohil. I'm an author, researcher, and data scientist, and currently undergraduate student at School of Technology, PDU in India. I'll be mentored by Henry Schreiner from Princeton University and Hans Embisky from TU Dartmouth for this summer. And my project is based on feature extension, inclusion, and rectification for Boost histogram. Now, a little bit of background on Boost histogram. Boost histogram is basically a Python package for Boost histogram, which is a C++ library, and it's basically used for creating histograms and profiles. And Boost histogram is a Python binding of the same. Now, in terms of usage, Boost histogram is basically used for any possible operation that you might think about a histogram. You can plot those, you can perform operations on them, you can do axis manipulation, and you have a ton of types of storages like double, integers, etc. And this and one of the main achievements of Boost histogram is that it was even included in the 0.20 release of PyDiode, which is an assembly port for CPython. And this has been possible because throughout the years, we have the project basically has worked upon adding more and more functionalities to it, more functions, and then making sure that the issues are rectified. And that will be the main objective or goal of my project. So in terms of goal and improvements, as I mentioned, the major aim of the project is to make sure that the issues, so Boost histogram, the Python binding, that's available on GitHub, which is where we have the entire project. And there are certain issues, there are several issues on there that we want to rectify so that we can improve the performance, we can extend the accessibility and the features that we have in the library. And that will be the main focus. Here are the 8 major issues that will be tackled during the course of the project. The first is visualizing the differences between the histograms. Now, histograms have several attributes to them. We have, of course, the contents of histogram. Then there's the sum of that. We have the types of rows, for example, regular. And then we have dimensions, we have size, we have certain attributes to histogram, and we want to make sure that we can directly, using the library, we can visualize the differences between histograms. Moving forward, we need to allow slicing on axis like we do in ND arrays. And if we just go through all the issues, then we need to also allow for that to be, we need to disallow basically the non-integer arguments for specific storages. For example, if we want to have a storage which only takes integers, then we don't want to allow any other inputs for the histogram. Then we also need to add the support for scalar in the histogram fill function. When we create a histogram object, we then fill it with the contents, and we need to add scalar support for that. Then we need to add operators for weighted histograms and accumulators. There are different types of histograms, and we need to add. So when we talk about operations, we have the basic ones like addition, subtraction, multiplication. Now these are already available for the basic histograms, and then we need to add operations for the weighted histograms and accumulators as well. The same goes for adding support of scaling, in addition of mean views. So so histogram is an object, and then we can convert that into an ND array. And then if we do that by viewing, so if we talk about the actual Python code, we have histogram, the variable for the created histogram object, and then we add dot view, which gives us the view for that. So when we have mean views, we want to add support for scaling that. Also, we have several accumulators in histogram in the library. So we need to add collector and efficiency accumulator in there as well. And finally, because we have so many functions, so many features, so many attributes, and there are several ways we can go through using the library, we need to make sure that we have good documentation for the same. We already have that, but we want to make sure that we even extend the documentation, and we also add in-doc notebooks, which basically means that we have Jupyter notebooks running inside documentation so that you can have documentation for a particular function, and you can execute that function inside the documentation using a Jupyter notebook that's embedded in it. So all of these features, once rectified, they will make sure that the extensibility, the accessibility, and the ease of use of library has been substantially improved. And that will be the main goal of the project. Thank you. Thank you for listening to me. And I would now take any questions you may have.
Okay, thank you, Jay. Next up, we have Surya.
Yeah, I'll just share my screen real quick. Can you see it?
Yes.
All right. So I'm Surya, and I'm working on improving the Kling interpreter's packaging system, the Kling packaging tool. So I'm a computer sciences major at University of Wisconsin-Madison, and I'm interested in compilers research, and my mentors are Vasil Vasilev and David Lange. So Kling is an interactive C++ interpreter that utilizes the REPL paradigm for fast development and testing, as well as the immediate feedback and runtime generated code. So Kling uses Kling and LLVM infrastructure, and as a result, it can use a lot of all the tool sets of those respective softwares. So it has many useful features such as compiler diagnostics, and in addition, it has its own command line prompt and just-in-time compiler. And Kling is also pretty useful for rapid development, and you can also embed Kling in other applications to enhance the application's functionality. So the Kling packaging tool is a command line utility that can build Kling from source and generate installer bundles for a variety of platforms, including Ubuntu, Debian-based platforms, Windows, Red Hat-based distros, Mac OS, and Unix platforms. So the CPT is a pretty useful and flexible tool, but there's several improvements that can be made to make the user's experience with the CPT more seamless. So improvements that, well, basically these are the goals for the project. So that's fixing platform issues, rewriting the CPT itself, rewriting documentation, and fixing miscellaneous issues. So for platform issues, this basically mostly entails fixing builds with LLVM, pre-built binaries, or LLVM installed from the package manager. And most of these builds are on Linux distros and Mac OS distros. And another major issue is fixing Debian packaging creation, and also fixing Windows builds. So in terms of rewriting the CPT, a full rewrite is going to happen with basically fixing up the old features, as well as adding some useful new features, such as specifying the number of cores that should be used when building Kling, and getting rid of non-functional options, which is basically just commenting out broken features. So rewriting documentation will come down to documenting the rewrite, so new features added and some fixes, as well as rewriting the old documentation for overriding variables such as which Kling Git branch to use, and which LLVM link to use. And miscellaneous issues really comes down to fixing software dependency issues. So CPT uses some pretty old software, so definitely just retrieving newer updates so that it can run without no problem. And yeah, thank you.
Thank you, Surya. All right, just wanted to thank everybody for coming. Good job in all the talks today by the fellows. We have another round of them coming up on Wednesday at noon Eastern. I'll send out an announcement for that. And that's all we have for today. So thank you.
Thanks, everyone.